Welcome to Unit 2, Topic 2, Video 4. And in this video we're going to be looking at sketching trigonometric functions. Of course, this is part of one or two dot points from the syllabus, but it is covered across 3 different exercises in the Cambridge text that we use. So there we have our homework, but also our learning goals and success criteria. So recall that, and we're going to break this down. This is all stuff from math methods. Recall that, first of all, our general function transformations exist in this way. So we have f and x defined as usual. So a function f of x could be a trigonometric function, could be a quadratic, could be an exponential, whatever it is. And then we have a vertical dilation and a vertical translation. These are the two components, dilation multiplied, translation added or subtracted, that happen outside the function. So you see they're beyond the reach of the function f of x. And so they happen vertically. And then we have our horizontal, b and c. Horizontal dilation is multiplied and horizontal translation is added or subtracted. Now there's a bit of nuance here. Remember, we subtract c because then it works the way we expect. Because in the horizontal, things are happening to the x rather than the y, or they're closer to the x rather than the y. So if we have a b horizontal dilation, well, it actually compresses a function by a factor of b. And if we have a c, we add c, it moves it to the left, that horizontal translation. Anyway, you should be aware that those 4 things exist. That's for all function, any function at all. If you do this, this is what happens. Now, here is a function that is, I've done a sine theta and then written x, so we'll fix that up. F of x, this is just a sine function. Now, I just want to show you that we get exactly the same results because we've got a vertical dilation, i.e. the amplitude, and a vertical translation, i.e. the midline or the center of equilibrium, whatever you call it. So we've got a relationship there directly with what we already knew. And then, of course, we've got a horizontal dilation, b, which turns out to be the period, or related directly to the period. And then we've got c, which is the phase shift, and the phase shift is the horizontal translation. Those 4 things that you've learned in your trig unit and methods, they relate directly to what you've learned in your just general function stuff. So it's important you've got that because we're now going to apply it to a set of new trig functions. The reciprocal trig functions, and here we are, secant, cosecant, and cotangent. Now, I don't want to scare you, they're really directly related. Sec theta is equal to 1 over cos theta. Cosec theta is equal to 1 over sine theta. Cot theta is equal to 1 over tan theta. Now, remember tan theta is sine over cos, so cot theta is cos over sine, the reciprocal of tan theta. I would suggest now that you have these written down on a sheet of paper and you pin them to your desk or to the wall next to your desk so you can reference them. You do need to know them. They're not on your formula sheet necessarily, so you do need to know them. But referencing them now, you'll learn them pretty quick. For me, I just remember that the letters don't go together as I expect. So sec goes with cos. Even though I desperately want cosec to go with cos, it doesn't. So sec goes with cos, and therefore cosec must go with sine, and therefore cot must go with tan. Anyway, let's have a look at some sketching examples. So here is sketching cosec. Cosec 2 theta minus pi on 3, 2 sec 3 theta, and cot theta. And we're going to do these by first referencing the original functions. So remember, this is equal to 1 over sine theta. And this is equal to 1 over sine 2 theta minus pi on 3. And this is equal to 2 over cos 3 theta. And this is equal to tan theta, which is equal to cos theta over sine theta. So let's have a look at these sketches. What I've done to prepare for this particular video is I've taken Desmos copies of the sketches, of the original ones here, these guys, so this guy here, so that we can build from that. Because we're going to build an understanding of the relationship between cosec and sine, for example. So let's scoot across to those sketches. Here's our first one. So hopefully you recognise that this is a sketch, incomplete. I haven't got arrows, you'll have to forgive me. Incomplete of sine theta. And we want to sketch cosec theta. And cosec theta is 1 over sine theta. So the first thing you can do when you get a question like this is go through and think about, where do we get 1 over 0? Because 1 over 0 is going to present to us an asymptote. So once I've worked out where we get 1 over 0, I'm going to plot down these lines that represent the asymptote. There we go. And 2 to go. Okay, so I've got 5 asymptotes. Now we have to think, what's going on in amongst those? So keep in mind that we get up to 1. So there's a nice easy point there, because 1 divided by 1 is 1. So cosec is actually 1 there and 1 there. And 1 divided by -1 is -1. So -1 there and -1 there. So I've got a couple of points. In fact, I might sketch my function in purple. So I'll plot any points that definitely exist in purple. Now what's happening, and I'll start my first segment. As we drop down from 1 here, the reciprocal of that number goes up. So actually cosec looks like this. And down here we get the same result but negative. So our purple function is cosec. And there we have it. Now, the next question asks us to calculate 1 over sine, so cosec 2 theta minus pi on 3. I'm going to do this on the same graph. It's a bit of a messy graph. And I'm not going to necessarily show my asymptotes all that well, but I will change colours to orange and recognise that the cosec 2 theta minus pi on 3, well, just like always, we just have a change in our amplitude, our period, and a change in our phase shift. So I'm going to start by sketching this version of sine, and then we'll just reciprocate it. So remember that compression factor of 2 has pushed the function in, but we do have a change of amplitude out to pi on 3. So this is it minus pi on 3, by the way? Yeah, minus pi on 3. So it goes forward pi on 3. So this is pi, which means that pi on 3 is about here. And that means our sine function starts there, but it's got half the amplitude. So whilst it goes to here again, it also goes to here. So it's going to be a little bit fiddly, but it's going to look like this. Like that. And here we might see I've got that point there, and I'm going down half pi. So half pi is there, half pi is there. I'm just going to stop it there because I think we've seen enough. And then cosec will be this light blue one. So it's going to just be, keep in mind we've got that asymptote here, and asymptote anywhere with where the sine is equal to 0. Cosec will just be the reciprocal. 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 So on and so forth. And there we have it. So the easiest way to sketch these functions, if you're asked to, is to go and look at, well, what is the original function? Because you know what? You've spent so much time sketching functions like that. Why not use them and then just do the reciprocal? That's really the easy way. But you could get the original cos function and apply these transformations as well. That's your other option. So let's do our last two. 2 sec 3 theta. So I've got a cos graph down here. And it's 2 sec 3 theta is 1 over cos 3 theta, but with a 2 here. So that 2 is like an amplitude change. And so let's sketch cos 3 theta first of all. That's just got a compression factor of 3. So it brings this point into there, and this point into there. And it repeats 3 times in between. So there, and then there, there, there. So this will stay the same. 3, 3, 3. This will come into a third of that, which is 2/3, so that's actually here. There we go. And so we've got a down, turn around, something like that. Now, at the risk of being lazy, I don't want to draw 100 billion of these graphs. So instead we'll go straight to our 2 over. So our 1 over is going to look like this. Just a really quick green 1 or 2. It's going to go like that. It's going to go like this. Asymptote still exists, but it's quite thin, so I'm having trouble drawing them really accurately, but obviously you would expand this out a bit. Our 2 over is just going to double this distance. It's going to take it a little bit higher, which actually means it'll start here. It doubles the distance from the x-axis. And there'll be a whole bunch of these guys. Oh, so that won't be there. It'll start here. And it will start at that peak, but at -2, so on and so forth, all the way along here. So I won't draw them all. Hopefully you see the point. Our last one that we need to sketch as example 2 is y equals cot theta. Now, cot theta is equal to 1 over tan theta. What did I do that? 1 over tan theta, which equals cos theta over sine theta. I just want to make a point here because 1 over tan theta is pretty easy to deal with because we've got 1 over 0. These points here, they're asymptotes. So I can sketch all my asymptotes on here. See, the asymptotes have shifted, which is interesting. But there's one little issue I have with the tan theta one. And that is that we can now easily recognize that that's small and positive, which means it's large and positive here. And then it comes down and gets really small. And then it does this back to the asymptote. So cot looks a lot like tan. But I've left that because this goes up here and tan has an asymptote there. What happens when we reciprocate an asymptote? We don't really know. I certainly didn't know when I started thinking about this question. So instead I thought, well, we could also look at it differently. And here we have cos x and sine x. And remember that cot theta, or cot x, is equal to cos x over sine x. So we could do this by just dividing cos x by sine x. And you see, whenever sine x is equal to 0, we have an asymptote. And so we just pump a little function down here like this. And then we go, well, where were the asymptotes earlier? The asymptotes earlier were when tan x was equal to 0, when cos was 0. Now, at that point, cos is 0 divided by whatever sine is going to give you 0. So it does make it clearer that we've got this function. And it goes through 0, which we kind of saw was what happened. But when you reciprocate an asymptote, we now know that you get 0. And there's my cot function. Okay, so that's our sketching. Hope that wasn't too rushed for you, but you can play around with those, and obviously you would try and be a little bit neater. And that's cot theta as well. So let's have a quick look at example 2. Sketch cos squared theta and then therefore sec squared theta, because remember sec squared theta will be 1 over cos squared theta. So there's cos theta. Let's think about what happens when we square it. The interesting thing here is that when we square 1, we get 1, and when we square 0, we get 0. When we square -1, we get 1, 0, 0, 1, 1, 0, 0, -1, 1, 0, 0, 1, 1. So we're going to get those particular peaks. And now, when you square a number that's between 1 and 0, well, that makes it a little bit smaller. So, for example, when you square this half, you actually get 0.25. And when you square this half, you get 0.25. When you square this root 3 over 2, which occurs about here, you get 3 over 4, which is about there. So we get something that still is curved, but it's just a little bit more boxy. So there's no intention for this to be the case, but it will look, I'm going to draw it again. It'll still curve, it'll just be a little bit more boxy. It'll look a little bit more triangular. Okay, and then when we say, well, what is sec squared theta? Well, that's just the reciprocal of cos squared theta, and so we get this with an asymptote of 0. But this time, they're all positive, and they're all just a little bit more boxy. Now, I have saved my Desmos page, so let's have a look at that little sec squared theta, what I've just done. I'd love for you to see the boxy nature of it. So if I start with cos squared theta, well, actually, it doesn't really represent it very well on Desmos, so let's change it to, because cos squared theta is just cos theta squared. Okay, so there's cos squared theta. You can see that it's now all positive, and it doesn't quite look as any more boxy, but if I put cos x there, you can see it's just a little bit more, it's dragged those values down. And lastly, let's do y equals, and sec x is there, there's our sec x, and of course we can square that, and it becomes a little bit more boxy. So I might even pop on y equals the original sec x there, and you can see that that's squared. Same asymptotes, does get to the asymptote eventually, just not quite as quick. Okay, well, that is everything I wanted to show you about graphing functions. That's all we've got. So you can go ahead and try some of those now. And so my suggestion would be, take a question, build your understanding through sketching each layer of that question to build up to the final answer, and then just check each part on Desmos as you go. It's a really easy method to make sure that you know what you're doing. All the best.